Hello everyone. In previous class, we discussed about the basics of electrostatic potential and electrostatic potential energy. Today, we will start with electric potential due to a point charge. So, our next topic is electrostatic potential due to a point charge. So as we know that here we have to take two charges, one as a source charge and another one as a test charge. So suppose a source charge Q is kept at a point O and we have to calculate electric potential at point P, which is at a distance of r from the source charge. Let test charge Q naught is at infinity. So we have to move this test charge Q naught at point P. Let this Q naught is moved at a point N, which is at a distance of x from the source charge. Okay, so first we will calculate the electric potential at point P, or we will calculate the value and then after we will calculate at point P. Okay, so now we can write the basic things that we have considered. So let Q is the source charge placed at point O. Okay. P is the point where we have to calculate electric potential. Let OP is equals to R. Let OP is equals to R. Okay. Again, let test charge Q naught is at infinity. Okay, so we have, what is the definition of electric potential? Electric potential is work done to bring this charge, work done to bring a unit positive test charge in the electric field of the source charge at any point. Let P is the point, at any point is known as the electrostatic potential at that point. So Q naught is at infinity on bringing it, let N is the point at a distance x from the source charge. Clear? Now we will calculate the numerical value. So this is the basic theoretical part. Now let another point M which is at a, so if we apply force, because these two charges are same, suppose some forces, so some repulsive force applied by this Q on this Q naught, let this will be the direction of force, because these two are similar charges, so direction of force will be repulsive. Clear? So if we move this Q charge towards this point M, so we have to do some extra work. Okay, let this distance is dx. Okay, now we have to do some extra work to move this charge Q naught in this direction. Okay, so N to M. Okay, so on moving charge Q naught from N to M, work done is, and we know that this work done is equals to force into displacement. So now we have to calculate, if this distance is very small, so we have to calculate the small work done, that means dW. dW is equals to force, the amount of force will be same. So this will be the external force that we will apply in this direction. So F into displacement will be dx. That this is our equation number 1. And these two are vector quantity. So as we know that this will be the scalar product, because this is work done. One more thing that we'll find over here, that this point is N. So here you can see this is the direction of force that is applied by this source charge on this test charge Q naught, and this is the direction of displacement vector. So angle between these two is 180 degree. Okay. Now if we'll solve it, what we have now, f dx cos theta. We know that vector A dot vector B is equals to AB cos theta, and vector A cross vector B is equals to AB sin theta. So here this is the solution for dot product. So f dx cos theta, and here you can see the theta value is 180 degree. So f dx cos 180 degree. What is the value of cos 180 degree? So we can find out with the help of graph of cosine. This is the graph of cosine. This is 0, pi by 2, pi, 3 pi by 2, 2 pi, 5 pi by 2, and so on. So here you can see at pi its value is minus 1. Here it is plus 1. So at pi its value is minus 1. So cos 180 degree is equals to minus 1. So we'll put this value over here. So it becomes minus f dx, because cos 180 degree is equals to minus. So dw is equals to, or dw is equals to minus f dx. That this is our equation number 1. Okay. Now we know that the force exerted between these two charges is equals to F is equals to 1 upon 4 pi epsilon naught q naught upon distance square. So distance between O and N is x. So this becomes x squared. Let this is our equation number 2. Okay. Now put the value from equation 2 in equation 1. So from equation 2 and 1, this dw is equals to minus, and here we will put the value of f, that is 1 upon 4 pi epsilon naught q naught upon x square into dx. Okay. So this is the small work done that we have to do to move this charge q naught from n to m with the displacement of dx. Now we will find out the total work done to move this test charge from n to p. Okay. So in that case, what we have to do? So on integrating both the sides, so dw is equals to, and the lower limit will be 0, upper limit will be w, and this whole term q naught 1 by 4 pi epsilon naught q naught will be constant. So minus 1 upon, or q naught upon 4 pi epsilon naught is constant. Here what we have now, 1 upon x square into dx. Okay. And we know that the integration of this can 1 upon x square into dx. This can also be written as x to the power minus 2 into dx. And we know that x to the power, the integration of x to the power n is equals to integration of x to the power n into dx is equals to x to the power n plus 1 upon n plus 1. So here it becomes x to the power minus 2 plus 1 upon minus 2 plus 1, which is equals to minus 1, and in numerator x to the power minus 1. So this becomes minus 1 upon x. Clear? So here it is. If we will solve it, we will get minus 1 upon x. And the lower limit, the initial point will be infinity, and up to where we have to move, up to at a distance of r. So the upper limit will be r. Okay. Now here if we will solve it, what we have now, integration of dw is w with lower limit is 0, upper limit is w, and here in this part minus q naught upon 4 pi epsilon naught. Here what we have now, minus 1 upon x, infinity to r. Clear? From here you can see the integration of 1 upon x square into dx is minus 1 by x. So now move this negative sign out from this bracket, so it becomes q naught upon 4 pi epsilon naught, and here upper limit minus lower limit, so 1 upon x, sorry, not x, the upper limit is r, minus 1 upon infinity, or q naught upon 4 pi epsilon naught 1 upon r minus 0. The value of 1 upon infinity is 0. So here this work done W minus 0, which is equals to W, or this W is equals to q naught upon 4 pi epsilon naught into 1 by r. So this is the total work done to move a unit positive test charge from infinity to a point P. Now we have to calculate the potential at that point. So how will calculate the potential? So electric potential at point P. So V, as we know that V is equals to W upon Q naught. In previous class we have studied about it. The value of W is Q naught upon 4 pi epsilon naught 1 by R, and whole divided by Q naught, this Q naught. So these two will be cancelled out, and value of V is Q upon 4 pi epsilon naught into R. So V is equals to Q upon 4 pi epsilon naught R. So at any point, so this is the electric potential due to a point charge at any point. Now one more thing that we have to consider, here you can see the potential is inversely proportional to R. Potential is inversely proportional to R. V is inversely proportional to R. That means on decreasing the distance, the potential will increase. On decreasing the distance R, the potential will increase, and on increasing the potential R, on increasing the value of R, the potential will decrease. Clear? So suppose we have a point Z over here, which is near to this source charge. So the amount of electric potential, let this is Vz and this is Vp, where Vz is the potential at Z and Vp is the potential at P. So as we know that in previous class we have already discussed about it. So amount of work done at Z, so Vz is always greater than Vp. Reason behind here, if this distance is R, let this distance is R1. So from here you can see this R is greater than R1, or R1 is smaller than R. The lesser the value of R, potential will be greater. So that's why this Vz is always greater than this Vp. Clear? That's it for today. In next class, we will discuss the electric potential due to dipole. Thank you.